In this segment, we'll talk about the background of the bisection method, that what the bisection method is based on so far as solving a nonlinear equation is concerned. So the theorem goes as follows. It says if we have an equation f of x equal to 0, then if f of x is real and continuous, and we find out that the value of the function at some point xl and then some point xu, if the product of those two values is less than 0, then at least one root lies between xl and xu. So that is the theorem on which the bisection method is based on. So if we look at it from a graphical point of view, so let's suppose somebody gives us f of x equal to 0, and we plot f of x as a function of x, let's suppose, and let's suppose the function looks like this. We are seeking this point right here because that's the root of the equation f of x equal to 0. So in this case, if we find out there is some point xu, let's suppose, and there is some point xl, and what we are finding out that the value of the function here is different from the value of the function here, or we can say that between these 2 points, between this point and this point, the function is changing sign, then we have at least one root between xl and xu. So although that's a qualitative way of saying it, but if we are writing a program, then the way to do it is to calculate the value of the function at one point and calculate the value of the function at the second point and see if the product of the two functions is negative, because if one is positive multiplied by another one is negative, do we get a negative number. So because if we have two negative numbers, then we get a positive number. If we have two positive numbers, we multiply it by another positive number, we'll get a positive number. And if we have a negative number and then a positive number, then we get a negative number for the product. So you can very well see that the function in these two cases is changing sign, but in this case, the function sign is not changing. So we can only talk about that when the function is changing sign, which is given by this product here, that the product of the two function values will be less than 0, then we can guarantee that there is at least one root which lies between xl and xu, provided of course that this function right here is real and is continuous. So some of the ways you'll find out that this particular theorem which we just talked about is misinterpreted is as follows. So let's suppose if I have my function, my equation like this, in my equation f of x equal to 0, let's suppose the function behaves like as is shown in the figure here, and let's suppose if I choose this as my one value of the function and this as another value of the function, what you'll find out is the function is not changing sign, right? And the value of the function here is positive, the value of the function here is positive, so I will get the value of the function here would be, or the product of the two function values will be greater than 0. But we have a root here and a root here, and one might think that that is the violation of that previous theorem. No, the theorem is only telling you that there is at least one root if the function is changing sign. It does not tell you anything if the function is not changing sign. So if the product is greater than 0, then you know that the function is not changing sign, and there may or may not be a root between those 2 points. Let's continue with these misconceptions or maybe misperception or perceptions. So let's suppose if I have a function here, and that is my function is a function of x, and my equation is of x equal to 0. Let's suppose I choose this as one of the points, and then I choose this as one of the points. Then the function value at xl times the value of the function at the upper limit, which is this point right here, is greater than 0. And in this figure, we don't find any roots between XL and XU, but this should not be interpreted as that, hey, if the function does not change sign, that there'll be no root between these 2 points. As we found out in the previous example, we had 2 roots between XL and XU when the function was not changing sign. So keep that in mind also, what the theorem is saying. It's only saying something if the function is changing sign. It does not say anything if the function is not changing sign. Let's look at another misconception which people have about the theorem which we just talked about. So let's suppose if I have the function in this equation, which is f of x equal to 0, the function which is on the left hand side right here, if this is how it behaves, and then I choose my lower limit to be this in the interval in which I say there is a root, what you're finding out here is that the value of the function at xl times the value of the function of xu is less than 0. And so there will be at least one root between XL and XU. It turns out that we have 3 roots between XL and XU. So people somehow think that there should be only one root between those 2 points. No, the theorem is only saying that if the function is changing sign between the 2 points, then there will be at least one root. It does not tell you how many of them will be there, but at least one root between XL and XU. One more misconception takes place in a function which is like this. For example, here we have f of x as a function of x, and let's suppose this is for the equation f of x equal to 0. And let's suppose if I choose this to be xl and this to be xu, the value of the function at xl times the value of the function xu is changing sign because it is positive here and negative here, but there is no root between XL and XU. So is that a failure of the theorem? No, it is not the failure of the theorem, because there are 2 other things which the theorem says, that the function has to be real and it has to be continuous between those 2 points in order to apply that theorem. So I'm hoping that it clarifies how we can apply the theorem, what the theorem says and what the theorem does not say. And that's the end of this segment.